Hello，大家見唔見到我？聽唔聽到我把聲？如果聽到睇到嘅話，請喺留言度講一聲啦。If you can see me, please leave a message so that I know that you are here. And then we will start in about 5 minutes. We will start in about 5 minutes. Hi, testing 1 2 3 4. Hi, testing 1 2 3 4. Testing 1 2 3 4. Testing 1 2 3 4. Hi, testing 1 2 3 4. Hello, Gilbert. Hope you can hear me. Because this is the first time, shall we wait a few more minutes? Hi, Jay. Thank you. Let's wait for another 1 minute and then we will start. For those who come late, they can always look at the presentation again. Hi. Hi, Anthony. Hi, Sunny. Start from the very beginning. So what's the subject today? The subject today is, let me just switch over to my control. Which is my control here. Okay. So the subject today is cosmic microwave background. Last time we talked about the universe eventually cooled to the point that it becomes transparent. At that particular moment, there's a flash of light. The the temperature of the universe at that time is shown as a black body radiation. So these lights should be very bright and should be very much in the very blue region, maybe even white. But because of the time dilation today, they haven't traveled to us for such a long time, and during this such a long time, the universe has already expanded many times, and therefore its wavelength have been stretched, and it is now in the called a microwave region. This is a picture of the microwave map. This picture is pretty high in its resolution. The color here, the red dot, the red area represent about 0.0002 degrees more hotter than the very deep blue region. The deep blue region is approximately 0.0002 degrees cooler. So the temperature difference here is not that great. The total temperature difference is 0.000 zeros, okay, 0 point and then 3 zeros, 4 degrees Celsius. And that is on the background of a temperature of around 8,000 degrees. So it is a very small difference. The image is what they call the Mulvady projection. That means this projection of our 360 sky is represented by equal areas. The average temperature today is about 2.725 Kelvin degrees. Now, Kelvin degrees is absolute scale. If we convert that into Celsius, then we will have to minus 275 degrees. So it is about minus 273 degrees Celsius. So it's pretty cool. Now, as I said, the warmer and the bluer region has a difference of about 0.0002 degrees. So this is what the Mulvady projection means, an equal area. That means it is perfectly absorbing all the lights coming on into it. It is black because it doesn't reflect any light, and that means it absorbs all the light. As it absorbs the light from the surrounding, it should be getting hotter and hotter. But if it is in equilibrium with the surrounding, that means it has a balance of energy. The light that is absorbed by the body, by that black body, is actually being radiated out again. Obviously, our human eye can't see it because it is in the microwave region or in the infrared region. And but the description of that one has been very carefully calculated. Here we have a example of the black body radiation. The photo on the left is in our visible light region, and on the right is an infrared camera, and the color there is a pseudo color. Pseudo color meaning that the color is actually being mapped to different temperature or hotness. So you can see that the black body is um, basically all blended with the background. But because the body itself emits infrared, and therefore the infrared camera can pick it up. The calculations for all this using classical theory gives us this general shape of the lights being emitted. From here, we see that if the object is around 3000 Kelvin. Again, we have to plus 273 degrees to it to add to the absolute temperature. So that will be around 3200 something degrees C. You see that is, to us, is almost in the red region, and that will give us a dull red. As the temperature rises to about 5000 degrees Kelvin, then it will cover almost the whole visible spectrum. To us, that is white. And if the temperature is even higher, then the peak will be closer to the left, meaning that will be a little bit more blue. Here is the representation of the color. On the bottom here, on the left hand side, which is red, the color of that the redness represent about 1000 degrees. As it moves towards to around 6500, it looks almost white because it's balanced in the visible spectrum. If the temperature becomes higher and higher, then it will look a little bit more blue. Of course, at the same time, the brightness will also increase. Now that is the black body radiation. So by the time the universe becomes transparent, we will expect it to behave like a black body, and that means it will try to show a curve, something similar to that one. Now, of course, the classical theory will work up to 5000 degrees, but we have formulas to give us what will be the shape of that curve at even higher temperature. So calculating that black body curve has been a major challenge, but eventually in 1901, Max Planck successfully calculated a acceptable curve. And of course, later on, it was Einstein building on the idea to give us the quantization of electromagnetic radiation itself. So the discovery of this cosmic microwave radiation, background radiation, is quite a story, actually. It involved a number of people. First of all, there are two persons in 1964 working at Bell Labs. Their name is Arlo Penzias and Robert Wilson. They were trying to develop some very sensitive antenna in order to pick up the radio wave bounced off from a 6-meter from a balloon. So the idea is that they want to measure the height of the balloon, and therefore they will use radio waves, send it to the balloon and let it bounce back and pick it up. To measure these very faint radio waves, they have to eliminate all possible interferences from their surroundings. So they remove the effects of radar, the radio broadcasting, suppress interference from heat in the receiver itself by using liquid helium, cool it to almost absolute zero. It's only about 4 degrees above zero at minus 269 degrees C. So they are trying everything to try to minimize the noise. But when they do whatever they can, they still find a very low, steady, mysterious noise that persists in the receiver. This resident noise is about 1,000 times more intense than what they would have expected. And it is very evenly spread over all sky. No matter in which direction they point, they always pick up this mysterious noise. And it's also present late at night. They were certain that the radiation detecting on the wavelength of 7.35 centimeters do not come from Earth, not the Sun, or not the galaxy. So they have been checking the equipment, even removing some pigeons nesting in the antenna, cleaning out everything, but the noise remained there. So they can only conclude that this noise must be coming outside from our own galaxy. Now, why they can confirm that it's outside our own galaxy, not from our galaxy, is by pointing at the directions outside of our galaxy. Now, remember at night, we look at the night sky, in a clear night sky, there will be a Milky Way, a band of bright lights, which represent many, many little lights in the sky located in the same region. That is our galaxy, the Milky Way. And therefore, if you point the antenna to other directions away from that galaxy, we should be picking up signals outside of our galaxy. And that's how they determine, because it's everywhere, whatever direction they point, and therefore they come to the conclusion that it must come from outside of our galaxy. So that is part of the story. On one hand, there is an experimental observation, and the observation is there is some kind of very funny noise coming from the universe. Penzias and Wilson doesn't know the source of it. On the other side, there's another few Persians, Robert Dick, James Peebles, and David Wilkinson. They are all astrophysicists at Princeton University. Well, not too far away from the two guys from Bell Lab, just about 16 kilometers away. And they were preparing to also search for microwave radiation, because they believe that if Big Bang is as expected, then on these people got Nobel Prizes, and then in 2019, the other one also get their Nobel Prize. So this is the picture. Now, remember, this is the current best observation. At that time, they were looking, to them, it was all uniform. These minor temperature differences wasn't there. So this is this picture, this photograph is a very late photograph. So let's look at how we get this particular photograph. Cosmic background, microwave background is a landmark evidence of the Big Bang theory. Now, if Big Bang do occur as what we have described, then when all the electrons come from there, we can calculate by how much it has already redshifted. Remember, the further away, the larger is the redshift. Now we are talking about a distance of 13.7 billion years. So that is very far away, and therefore the redshift is huge. So the whole spectrum has shifted from the ultraviolet region into the current microwave region. Okay, that's exactly what it's talking about. The photon that existed at the time of the photon decoupling has been propagating ever since, through growing fainter and less energetic. Since the expansion of space causes wavelength to increase over time, and this is exactly what we are looking at. Okay, how we get all these fine details of this cosmic microwave background? As soon as we have discovered this CMB, then experiments are being done to try to find out a little bit more about this microwave background. So they launched different satellites into the sky in order to give a quantitative large-scale differences in all these microwave region. So these are, the first one is COBE, C-O-B-E, a Cosmic Background Explorer, and that's launched in 1989 to about operate until 1996, and it is the first in outer space, further away from Earth, outer space detection. Later on, there are other more sensitive experiments like the Boolean or the DASI, D-A-S-I, the degree angular scalar interferometer, or even the more recent one, the cosmic background imager, CBI, etc. They are trying to measure to better and better accuracy of that background radiation. So 2001, another project, and then the WMAP, which is the highest resolution we get at the moment, is launched in 2001. And finally, we have all these different detectors, and then come up to the current image. So these are a little bit of history of the development of all these things. So based on the 2013 data, we now come to conclusion that ordinary matter only represents about 5% of the universe. There's another 26.8% being dark matter, which we can't see, we can't detect, and about 68.3% dark energy, which we can't see, we can't detect. So there's a lot of things we do not know. But from what we know is this cosmic microwave background. There is a very subtle fluctuations, and this picture is taken when the universe is about 370,000 years old. So it is the earliest picture we can ever take, and this is the difference. Initially, the COP look at it is almost like uniform, except a little bit of different color there, and then improve upon, and then later on the Planck is what we are seeing in the sky. Now there are several questions here. When we are doing this, we are being interfered by our own galaxy. So the measurement have to subtract out the galaxy, our own galaxy, in order to get a map. So this is what they have done, and the map I have shown before, sorry, this map has already subtracted out the our own galaxy, the effect of our own galaxy. And what we are seeing here is some rippling effects. This rippling effects is just like we have a water on the ocean, and there's any disturbance, there will be a ripple out, or the wave on the ocean floor, on the ocean surface. So we believe this particular image is due to very minor oscillation. It's kind of like sound in the universe when it was expanding. We'll expect during that time there will be something like sound waves also propagating, like wherever. So although the universe is pretty uniform, but there will be some ripples like that, and that kind of ripple probably produces this dark red and dark blue region. That's one possibility. Another possibility is very fine scale universe. So this is another area we do not know, and to have that, we need even higher resolution of this map. So I think the scientists are going to find out a even higher resolution of this map in order to understand more about the beginning universe. Okay, and let me look at some of the messages coming in from you guys. I need to go to my other computer. Sorry, that might be blocking the scene. Hand up. Okay, not much message here. So I don't know whether people can understand what I have been saying. So if you have any questions, you are welcome to type it into the chat, and I'm going over there to have a look. Where's my it's the PowerPoint. Yeah. Okay, anyone have any questions? You can ask me by typing it into the chat area. Anyone? I think I need to go back to another computer in order to do that. So just excuse me, this computer might be blocking your view. Let me just put it here. Hopefully it doesn't block too much. Okay, anyone with any questions, you are welcome to ask. And I think I better put on my headphones in order to listen better to you, because if I turn on the speaker here, it will have echoes. So I need to put on the microphone. Okay, this is the first online class. I don't know how everybody feels. not too many people are actually watching at the same time. I think I might have lost many of you because of the muck up in. I better don't listen to myself because there's a time delay and I'm distracted by so I take off my headphones. But okay, anyway, if no more question, then I better finish this live event and then let me get prepared for the next one because I'm still learning how to do it. So see you in the next session, and of course this event, the whole presentation will be available for people to watch anytime later. So thank you very much and see you guys. Bye. Of course, this event, the whole presentation will be available for people to watch anytime later. So thank you very much and see you guys. Bye.